Okay, so here we are with lecture 12 of Physics 3113, and today we're going to continue our discussion of Bose-Einstein condensation that we began and covered in lecture 11. So today I'll just go over the results again that we derived in lecture 11 briefly. We'll have another look at the chemical potential for the Bose gas. And then I'll talk a little bit about the Bose-Einstein condensation and how it relates to quantum levels or quantum physics a little bit. And finally, we'll go to the heat capacity of the ideal Bose gas, and we'll discuss that. And finally, I'll talk about Bose-Einstein condensation phenomena in various systems. Okay, so last time we looked at the number of bosons not in the ground state, so the number in the excited states below this critical temperature that we derived before. And remember, we got the critical temperature by imagining that we didn't have to worry about the ground state, and we would try to maintain the total number of particles by adjusting the chemical potential, and we found that that was not possible below this critical temperature. And so then we went back, we separated out the system into ground state and excited states, and we realized, well, let's just calculate below TC what the number in the excited state will be, which will be less, of course, than the total number. And we do that just, of course, by this integral over the density of states. And we also remarked that since we had already found the critical temperature, we could write the density of states in a more convenient form that involved the critical temperature, like we've done in the past when we studied fermions. And that gives a constant out front here, which is the zeta function and the gamma function. They're just numbers, and we discussed what those numbers were in the last lecture. And so now we're going to look at this again below Tc, some arbitrary temperature T below Tc, and to find a number in the excited state. Of course, this integral, of course, leaves out the ground state at energy epsilon equals 0. But we can find the number in the excited state this way, and it will be less than. Of course, this factor will end up to be less than 1, right? So and when we do that, so we just look at this integral, and this integral, it's helpful to change variables again to this dimensionless x, which is epsilon over kBt. We did that sort of last time. We did all this last time, by the way, if you want to review that again. And we can complete this integral, and of course, this factor turns out to cancel out these factors because we already did that before with finding the critical temperature. And in the end, we find that the number of particles in the excited state is n, and as we said, it must be some factor that's less than 1. And of course, when t is less than Tc, this is factor less than 1, and so to the 3/2 power, it will be less than 1. And this tells us that if we look at the fraction, which is the number of particles in the excited state divided by the total number, it's basically T over Tc to the 3/2 power. And so, of course, the remaining particles must be the fraction in the ground state, and that gives us then this equation for the ground state occupancy, or the fraction number of particles in the ground state that has this dependence. And we plotted that, and it looked like this. It rises quickly from the critical temperature and goes to 1. Okay. And for T greater than the critical temperature, well, the number in the particles in the ground state is negligible, and we don't have to worry so much. We can just use that integral to calculate that. But below this critical temperature, of course, as shown in this plot, the number in the ground state increases rapidly, and this is a phenomenon of Bose-Einstein condensation. And the way this grows indicates that it's a continuous second-order phase transition, and this condensate fraction, as we call it, the fraction in the ground state, is a kind of order parameter of this low-temperature phase. If you want to think of an analogy, you think about the magnetization per spin for something like the Ising model or some other spin model that grows below its critical temperature. That's the order parameter for the kind of spin model, and this condensate fraction is kind of the order parameter of the low temperature phase for this Bose-Einstein condensation. And we also mentioned that particles in the condensate have zero energy and zero momentum, and because of this, they don't contribute to pressure or viscosity. And we'll discuss this a little bit at the end of this lecture when we talk about superfluid helium-4, which has zero viscosity because it's it's a kind of Bose-Einstein condensation, at least approximately. And yeah, and also I mentioned last time that Bose-Einstein this condensate, it's not really like a liquid so much. It's a very special kind of condensate, and there's no spatial separation in the phases with different properties. So it's not like in a liquid to gas that if you have a container and you have this condensation, you have the liquid sitting somewhere at the bottom of this vessel and the gas around it. It's not like that. It's all intermixed, of course. Okay, so so that was all from the last lecture, and I just wanted to review. So let's look once more at the chemical potential below TC, because we discussed this before. So now that we've found the condensate fraction below the critical temperature of this form, we can separate. When we also had separated out the condensate fraction just by this Bose-Einstein distribution function, then we can actually solve for the chemical potential. And we argued it would have to be close to zero and it would remain close to zero. And we argued before that it would be negative and close to zero and sort of linearly decreasing with temperature at very low temperatures. That's what we argued before. So now that we know this, we can turn this around and of course solve for the chemical potential. And just solving this equation, you get this form here. This logarithm of this factor here, and for if the temperature is very, very low, we'll approximate this. We'll just take this term's going to be 0 very quickly, and so we'll just set that equal to 0 as a low temperature approximation, and we have mu over kt, or really Boltzmann's constant, kBt, is a natural logarithm of n divided by n plus 1. Of course, that factor is negative because this is n plus 1 is larger than n, so this is smaller than 1. As we said, it's negative. And we solve in this limit, and we see that as we argued before, it's negative, close to 0, and then the limit that n goes to infinity becomes, really at 0, which is kind of the thermodynamic limit. Right. And of course, that's, well, let's just see how it goes for large n. We'll just write it that way. And if we just rewrite the argument of the logarithm here as 1 plus 1 over n, then of course this term is going to get very, very small when n goes to infinity. And we can approximate the logarithm. So the logarithm of 1 plus some small factor is that small factor. And we get this dependence for large n. So for large n, the temperature dependence, so as in the thermodynamic limit, it's getting closer by 1 over n, and it's also getting closer to 0 linearly with the temperature decreasing. And that's just what we argued at the beginning of this lecture. We did some hand-waving arguments, and we had n0 here, the number in the ground state, and we said, well, we expected n0 to be approaching n, and we sort of used that at the basis of our argument at the beginning of, so actually it was the beginning of lecture 11, actually. You have to go back and look at lecture 11 for that. And so it's good to see this, it's good to see this come out of what we found for the actual dependence of the number of particles in the ground state. Okay, so another aspect that what's interesting to look at regarding Bose-Einstein condensation is this kind of connection to, I kind of call it the quantum connection, but it's really, there's actually lots of connections to quantum physics that we won't explore. This is a rather simple one, but it's really worth pointing out. So we found the number of bosons in the excited state, just as I presented in the last a couple slides ago, as total number of bosons times this factor T over Tc to the 3/2 power. And if we plug in the value of Tc we found, we just write it this way. It's proportional to the volume, of course, and to this sort of factor. That's just where we've taken, this is basically the inverse of Tc, this factor here. Well, we've pulled out also this constant, this zeta of 3/2, which was, I think, 2.61 or something. It's just some number. Anyway, now if you look at this factor inside this brackets, inside these parentheses here, you realize that you might recognize that it's something like the inverse. It's like the inverse square of what's called the thermal de Broglie wavelength. And I think you had that in part 1 of the course. It's in chapter 4 of the textbook if you want to have a look at that again. But the thermal de Broglie wavelength is just given by Planck's constant h divided by the square root of 3 times the mass times kBt, right? And so as t gets really small, this factor is getting really, really large and large and large. So what we see by recognizing that factor is that the number of particles in the excited state, and remember that above Tc, essentially all the particles are in excited states because there's very little that the factor, the ground state doesn't really contribute above Tc. So we can think of this as all the particles basically. Well, we see that the number in the excited state from this is sort of like volume divided by the thermal wavelength of these particles cubed, right? So this is the total volume, and this is kind of like the volume that each particle takes up, right? It's a kind of wavelength of these particles, and so of course we expect the number to be proportional to that, and you can plug it in if you like. You just get these prefactors here, right? It's from this equation by plugging that in. So you can imagine kind of what's happening then. That is that you could say, well, if I put in the critical temperature, I get the value of the de Broglie wavelength at this critical point, and what would that correspond to, right? And so at low temperatures, this becomes this thermal de Broglie wavelength can become very, very large. In fact, if you keep going to low temperatures, it becomes as big as the container that you have the bosons in. But remember, if we took the value for Tc, we could actually plug Tc into this thermal de Broglie wavelength and work out what we get. And what you'll find is just this: is that the critical value of Tc means the critical value for this de Broglie thermal de Broglie wavelength, and it's some few times or some several times V over n. This is the volume divided by the number of particles. So it's kind of the volume per particle, right? Sort of the average volume that one of these bosons occupies times some factor, of 8, right? And so what this is saying is that as you go to low temperature, when the thermal de Broglie wavelength cubed, which is the volume that a boson occupies, is several times the volume per particle, then that's where this transition occurs. And what that tells you, it basically tells, roughly speaking, that this transition occurs when the particles start to fill each other and start to overlap, right? So that's an interesting way then to look at the critical temperature and what's happening. Now, there's much more regarding quantum behavior of Bose-Einstein condensation. It's a huge, really interesting subject because what you find is in this ground state, all the particles are in the same state, and in fact, this ground state behaves quantum mechanically in a very coherent manner. It's like this order parameter, which I mentioned was like the number of bosons in the ground state. It can also be thought of as a kind of a macroscopic wave function that describes the all the many particles that are in the ground state, and they all have sort of in a rough way of speaking, the same wave function. And in fact, that can have a phase, and that can behave. You have a lot of effects that are based upon quantum coherence of these condensats, and that goes for superconductivity as well. The fact that, which we'll discuss at the end, superconductivity is not really ideal Bose-Einstein condensation, but it involves something very similar, and the fact that the ground state has a large number of particles described by essentially the same wave function leads to some quantum coherent behavior, and it's the basis, for example, of superconducting quantum bits. But that's kind of a side story. But I just want to point out to you this way of looking at the transition temperature, the critical temperature, and the transition, and as a way of thinking, and point out some other things. All right. So let's continue then. Let's calculate now the heat capacity of the ideal Bose gas at constant volume. So we won't change the volume of the system, and that's called CV. Okay, well, first thing you must ask yourself is, how do I get the heat capacity? Well, of course, I have to find the mean energy of the Bose gas. And then I look at its temperature dependence, and I take the derivative. So heat capacity means find the mean energy, and then see how its temperature dependence. So, but first, before we go run off and calculate things, let's kind of think about it physically from a kind of conceptual point of view, right? And so we saw that the below the critical temperature there was a large number of the particles that are in the ground state, which grows as we lower the temperature, and then there's the rest of them were in excited states, this N sub E, and we can think of these as normal particles. It turns out that they behave more or less like usual particles in a box, or ideal gas particles, let's say, right? And so for the temperature less than the critical temperature, we might argue that well, if everything's in the ground state and we've called that zero energy, of course that's going to contribute zero to this. So we might argue that, well, only the normal particles contribute to the mean energy and its temperature dependence, right? So we might expect roughly, of course, that the mean energy is number in the excited states times kBT, right? As you might expect for an ideal gas, let's say, or this is sort of an equipartition. If you remember, we discussed Equipartition Theorem a few lectures ago. And so we substitute in then this expression for the number in the excited states that has the N times T over Tc to the 3/2 power, and then times T here. So we just substitute this, and then we get just move the Kb over here, and of course we have something that goes like, well, this is well, actually I unfortunately I dropped the NKB, should go on this side of the equal sign as well, but the point is the temperature factors now are T to the 5/2 times Tc to the 3/2 divided by Tc to the 3/2. Then if we take the derivative, of course, we bring down a factor of 5/2, and we the numerator becomes T to the 3/2 again. So in the end, we get the heat capacity that we expect. If we just thought, well, it's just the normal particles contributing, and it's 5/2 in kb times T over Tc to the 3/2, right? And well, turns out that will be a good estimate. We'll actually now we'll calculate that, expecting something like this, right? Well, of course, to calculate precisely, we have to integrate over the density of states times the energy, and find that, and integrate from 0 to infinity, as we normally do. And we're going to use this trick again. Remember, we found the density of states in this more convenient factor, which is A times epsilon to the 1/2. And when we find the mean energy, we multiply by another factor of epsilon, so we get epsilon to the 3/2 here. And this constant A we found, by expressing the density of states in Tc rather than this more complicated factor. That's what we found. We used that at the very beginning of this lecture and in lecture 11. And so let's do that. Well, we still have actually a pretty not so easy to do, let's say, integral. Of course, it always can be done on a computer. But let's first, to get some understanding here, let's look in the low temperature limit. And as we've argued many times before, in the low temperature limit, this inverse fugacity, lambda to the -1, it goes to 1, and then we get this integral here, and of course we do the usual change of variables. That brings out the beta to the 5/2 here, because we've got, when we have x, when we substitute epsilon is x over beta, we get 3/2 from that factor, and another power of 1 from that factor, and that's why this beta to the 5/2 is there. And now we have this integral over x. Oh, I made a little mistake there. That should be an x, of course, as well. I'll fix that before I post these notes up to Moodle. And we haven't quite seen that integral before, but there's actually a result. It's in the textbook, and you can find this on the internet, and other people have studied these kind of integrals a lot since the early days. And whenever you have an integral, and I can't believe it, I had this, I didn't catch that from when I was writing these notes up. This, of course, should be an x, but integrals of this form, when you have x to some power and you express that z minus 1, e to the x minus 1 over dx, you get basically a product of a gamma function of z and the zeta function of z. And of course, these are just numbers, right? These are just numbers. And remember, we had this a here that we found from the number constraint. And now if we complete this integral, we get something that's fairly easy. In fact, it's very much like what we guessed up here. It's just that we have different factors out here. And these are just numbers and can be evaluated, by the way. So do I have those numbers there? I don't have these numbers, but you can look them up. I think there's actually a table. We've already looked up the values for here, and like this was, I think gamma 3 of a square root of pi over 2, or was it pi squared over 2? They're just numbers, and if I collapse all these numbers in the 5/2 together, I get 1.93 to 3 significant figures. There's more if you want, but because these are irrational numbers. And what do we get? Yeah, about 2 in kb times this factor. And what did we have before? We had 5/2. So this was pretty close, Well, that's for low temperatures, and that's for low temperatures. Now, what do we mean by low temperatures? Well, we'll come back to that because we had to make this approximation to actually get this integral in an easy form at low temperatures. We don't mean just T below TC, by the way. We mean when x is small, you can see we need beta over epsilon to be small. But anyway, we'll come back to that. Well, what about high temperature? What do we expect at high temperatures above the transition, and where the thing is behaving essentially classically? Well, classically, of course, we would have 3/2 in kb, right? That's what we get. Remember, if our arguments about the equipartition and that at large temperatures, Bose-Einstein and Fermi gases behave like ideal gases. So that's something that is increasing with temperature, and that's something that's flat with temperature. So on the basis of this argument, we would expect some sort of kink or discontinuity, or maybe both, at this critical temperature. But we have to be careful, as I said, because this approximation of the inverse fugacity being 1, it actually fails when the temperature T over Tc goes to 1. It's not quite good for that. But and it's no problem. We just have to evaluate this integral, this integral here more precisely. And you can always do that numerically. There's always other approximations you can use as well, by the way. There's a sort of systematic approximation, like the Sommerfeld expansion we did when we studied fermions. But so it's no big deal, really. But you get pretty much the general behavior. What is found is shown in this plot. At low temperatures, you do have this increasing heat capacity that sort of increases like that, and then at the critical temperature, this is from the book. He uses T0, and I'm using TC. So, but this is at 1, and then instead of going flat, it actually just falls off slowly this way as well. But you can see it approaches the classical limit here as we go to high temperature, right? This 3/2 here. So yeah, so this is the usual way we like to plot the heat capacity, and we divide it by n, number of particles, and kb. So so it's dimensionless. And yeah, so that, that's what the heat capacity does. And we notice that it does have a sort of cusp or a kink, no discontinuity though, but it has a kink here. And as we mentioned with the order parameter, or the condensate fraction at low temperatures, this kink is generally what happens at a second order or continuous phase transition, that you get a peak in the heat capacity. In fact, you may have seen that also in sort of magnetic models for the magnetization, when the specific heat also has a kind of peak at critical temperature. In magnetization, usually you get a peak and a discontinuity as well. But it's typical for, this is very typical for the specific heat or other sort of what we call response functions at second order phase transitions. Okay. Well, this is a really interesting phenomena, and in fact it was predicted a very, very long time ago, in the early part of the 20th century, that there was this idea of Bose-Einstein condensation, and it took a very long time for people to really experimentally realize this. And even though, that being said, it was what we know as superfluidity was discovered in liquid helium, which we'll discuss here on this slide and the next one, and it was suspected because of the properties of superfluid helium at low temperature, the fact that there's no viscosity and other things, that maybe it was some related to Bose-Einstein condensation, which it is, but it took a while kind of to work that out. We'll come back to other types of condensation phenomena that are analogous or contain some of the same physics as Bose-Einstein condensation. Experimentally, though, it's hard to reach an ideal Bose gas because particles interact, and in the ideal Bose gas, we assume no interaction. And you can imagine if you have something where all the particles are getting down into the same state, the ground state at zero temperature, ignoring the interactions becomes a bit problematical, let's say. So anyway, well, atoms of 4 He, and so of course you find with helium there are two isotopes. There's we call them helium-3 and helium-4. Helium-4 is the nuclei are 2 protons and 2 neutrons. So it's an even number of fermions, and so helium-4 is a boson. And of course it has an even number of electrons too, if you want to consider molecular, which is important here. So they're bosons, and they're quite they're actually very, very weakly interacting, which is why helium has such a low boiling point, and so we think we might expect it, to resemble an ideal Bose gas. And if we used our result for TC, we predicted the critical temperature, and it depended on Planck constant squared, the mass of the particle, Boltzmann's constant here, just this number factor, and more importantly, the density, the number density to the 2/3 power. If we use that, we know the atomic mass of helium-4, and we know the density of liquid helium. We could predict the Bose-Einstein condensation temperature, and we get 3.13 Kelvin. Well, liquid superfluid helium, liquid helium-4 does exhibit a superfluid transition, and it actually occurs at 2.17 Kelvin, a bit lower than this estimate, and it's called the Lambda transition. And the reason why you hear it called the Lambda transition and why it's usually the critical temperature is denoted T sub lambda is because if you look at the specific heat, in that case, the specific heat of liquid helium-4 has this behavior, this really sharp peak, and it actually has a little bit of a discontinuity up here, and it looks like the Greek letter lambda, so that's how it got the name, the Lambda transition. And so on this plot you see here's the Lambda transition for superfluid helium transition at 2.2 Kelvin. And this is the heat capacity. That's what it looks like for liquid helium. And this is what we calculated for the Bose gas. And this is where the go, if we would predict it. So there's obviously, it kind of looks like it's Bose-Einstein condensation, which in a way it is. It's just more complicated, and it gives a different heat capacity. And the other key observation was actually the behavior of the heat capacity down in here, right? And we predicted, so if you go and look back here, we predicted the heat capacity to go like T over Tc, or at low temperatures go like T to the 3/2 power, right? And here it goes like down here, what's found experimentally, it's much sharper. It goes like T to the cubed. And that suggests that phonons are important. Well, basically, in fact, next week when we study phonons and we study the heat capacity of solids due to phonons, we'll derive this, T to the 3 dependence of specific heat. So, what does it tell you? I mean, I guess researchers in the early days realized that, that helium-4 was not an ideal Bose-Einstein condensate, and even though there's a lot of similarities, and it's due to the interactions and phonons, which arise because atoms attract and repel each other and like to sit at a certain distance. Basically Lennard-Jones potential, if you heard that for something like helium, is important and has a lot to determine the properties of this. Nonetheless, it is a type of, if you can think of it, it is a condensation of bosons. Okay, so below this lambda transition at 2.17 Kelvin, this liquid helium-4 exhibits superfluid properties. And we mentioned that in principle, a Bose-Einstein, or not in principle, that a Bose-Einstein condensation, that the ground state as the condensate was non-viscous, right? So superfluid helium-4 does exhibit that, and in particular, you have flow through a small channel that non-viscous flow that would actually prevent the flow of a normal fluid. So you make a pore small enough that a normal liquid would, because of viscosity, wouldn't be able to go through it. Then superfluid helium has this property of what we call a superfluid. In fact, this is a very annoying property of a superfluid helium if you use it for low temperature experiments. And for example, in my lab or a lot of labs here, and these days a lot of the low temperature apparatus we buy is made pretty good. And in the old days, or if you have a piece of low temperature equipment that uses liquid helium and you go down to very, very low temperature, and for example, it's old, it's very annoying because sometimes you have a leak because you have some small crack somewhere, and when the liquid helium becomes superfluid, it will leak right through it, and it's very hard to diagnose because you have to warm up to look for things. Then you're not going to see this, and then so you have to cool everything down again, and you get this super leak, and I could tell you stories about people that worked for months trying to find super leaks in their equipment. Anyway, but it also has, these properties are also extremely amazing as well, and we'll get to that. That's only one of them. So the message is, though, and we're certainly not going to cover this in this course, but a detailed theory of superfluid transition in liquid helium-4 has to take into account these interparticle interactions. And it took some time to actually develop this theory. This was still being worked on, well, a lot maybe in the last century, but it's still, the details, people still work a lot on certain aspects of superfluid helium-4. And there's actually been a bit of a renaissance in it now that people can make nanostructures and make nano-mechanical and micro-sized resonators, and now they're studying the properties of mechanical motion when it's in liquid helium and there's no viscosity. It's very, very interesting work that's just happening, sort of, like I said, a rediscovery of some of liquid helium-4 effects that I know several people are doing, including some in Australia. Okay, but I really want you to watch this because you're going nowhere over Easter apparently, and there is this really, really excellent film on superfluid helium-4. It comes from the 60s, 1963, and it's this professor Alfred Leitner. He was at MSU, Michigan State University, and he made this film, and I remember watching this when I was an undergraduate. It totally blew me away. It was totally amazing. And I put a link here. You can find the whole film in several parts. There's a playlist on YouTube. Let's just click it. We'll watch a little bit of it. Let's see if it'll allow me to do it. Allow.
Level of the air to the level of the air. Okay. Listen. Good. Just draw.
We just made a transfer of some liquid helium out of a storage tank into our own experimental equipment. Helium is a remarkable substance. It has two different and easily distinguishable liquid phases, a warmer and a colder one. The warmer phase is called liquid helium-1, and the colder phase, liquid helium-2. The two phases are separated by a transition temperature, known as the lambda point. When liquid helium is cooled down through the lambda point, a transition from helium-1 to helium-2 is clearly visible. We will show it to you later in this film. The two liquids behave nothing like any other known liquids, although it could be said that helium-1, the warmer phase, approximates the behavior of common liquids. But it is helium-2, the colder phase, which is truly different. Because of this, it is called the superfluid. The temperatures involved when working with liquid helium are quite low. Helium boils at 4.2 degrees Kelvin, under conditions of atmospheric pressure, and the lambda point lies at roughly 2.2 degrees. Note that this corresponds to minus 269 and minus 271 degrees centigrade. The properties of liquid helium that I've just been telling you about are characteristic of the heavy isotope of helium, helium-4. The element occurs in the form of two stable isotopes. The second and lighter one, helium-3, is very rare. Its abundance is only about 1 part out of 10 million. Pure liquid helium-3 is the subject of intensive study at the present time, but so far no second superfluid liquid phase has been found to exist for helium-3.
Okay, did you catch what he just said there? He said no superfluid phase had been found for helium-3. And that's because this film was made in 1963. In fact, superfluidity in helium-3 was discovered not long after that in 1971. So be sure to watch this. It's really great. I think you'll enjoy it. So, okay. And we'll just mention that, as I said, superfluid phases, two superfluid phases actually were discovered in 1971, and they both occur around 2 millikelvin. That's 10 to the 3. A millikelvin is 1,000th of a Kelvin, 10 to the minus 3 kelvins. And helium-3 is a fermion, so superfluidity in helium-3 occurs by pairing of fermions to form composite bosons. And I was just recently I've been reading a lot about superfluid helium-3, and it's incredibly complicated system. It really, I have to say, it really makes my head spin. But anyway, we'll talk about other types of condensation in the next slide. But do watch this film if you have time. I highly recommend it. Well, there are other systems where something like Bose-Einstein condensation is found, and of course, you probably know there are things as superconductors, and most elemental metals and lots of alloys superconduct at low enough temperature. And superconductivity, the usual kind that we understand in elemental metals and alloys, and maybe, in fact, all types of superconductivity involve pairing of fermions to form what are known as Cooper pair bosons, named after a guy named Cooper. Now, superconductivity was discovered in 1911. That was by Onsager at, not Onsager, I forget the guy's name now, at Leiden, Onus. Yes, Onus. But it took more than 45 years before a correct microscopic theory was formulated that really described how fermions paired up in Cooper pairs and became superconducting. And this theory is known as BCS after the authors Bardeen, Cooper, and Schrieffer, who published a paper in 1957 about this microscopic theory, and they shared a Nobel Prize in 1972 for this work of superconductivity. So superconductivity in conventional metals is well understood in terms of BCS pairing, and the pairing is due to a really interesting effect when you have an effect of attraction between electrons due to phonons. However, you've probably heard there are things called high-temperature superconductors. Starting in the mid-80s, it was the cuprates, and nowadays they're the iron ptychnides and other materials. And these are still an open problem and subject of ongoing research, just understanding the theory, for example. And starting about in the 90s, so the history of Bose-Einstein condensation in the ideal sense was very, very long, and for years people were trying to achieve a Bose-Einstein condensation that was nearly ideal, and did not involve, for example, pairing like in helium-3 or superconductivity, or that was more ideal, say, than in liquid helium-4, where there's strong interparticle interactions. And so this was finally achieved, actually, starting in 1995 with trapped atoms that are trapped in magnetic traps, such as rubidium-87, and they laser cool these to microkelvin temperatures. And there's a problem about Bose-Einstein condensation in this system that it's on your assignment. basically, this type of Bose-Einstein condensation, which is really truly Bose-Einstein condensation, was discovered by Cornell, Wieman, and other co-workers at, I think this is a Joint Institute in Boulder, Colorado. It's called GILA, and they discovered this in 1995 by cooling a gas of about 2,000 rubidium-87 atoms in an electromagnetic trap. And about 4 months later, another group led by Wolfgang Ketterle at MIT also achieved a Bose-Einstein condensate using sodium-23. And Ketterle's condensate had more than something like 200 times more atoms than the 2,000 here of Wieman's group. And of course that meant, as we've seen, the critical temperature depends upon the number. So if the volume per particle is smaller, then of course the temperature can be higher, and you see the transition at a smaller de Broglie wavelength, right? We just argued that in the beginning of this lecture, and so that's why. So getting more particles meant a higher transition temperature, and I believe the transition temperature there was, well, I don't remember the temperatures off the top of my head, but anyway. And finally, in 1998, trapped atomic hydrogen was used to achieve Bose-Einstein condensation at a temperature about 50 microkelvin. And I knew a professor myself when I was a PhD student who had worked on this for maybe over a decade. It was a very difficult experimentally to achieve, and someone finally achieved it in '98. There were a number of groups racing after that. Anyway, so, well, that's it for today's lecture on Bose-Einstein condensation and related phenomenon. And I'm going to, this will be your last lecture for this week, and then we'll pick up next week when we look at photons, electromagnetic radiation in a cavity, and black body radiation, and then we'll also look, finally we'll wind up the course by looking at phonons. Until then, have a good Easter, and good luck on all the assignments you have. I know you have a lot to do, and if you want to take a break, be sure to watch that film on liquid helium 4. It's really cool.